another Exploring Ethics Forum program. I'm Mike Kalichman. I am Director for the Center for Ethics in Science and Technology. And some of you already know that, those who have been here before. How many of you actually are here for the first time tonight? So that's it's more than half. I know that a fair number of you are here with the Association for Integrated Studies meeting that's being held in San Diego. That's a rare event, I take. I don't know how often it's had their annual meeting in San Diego. No, the first time. This is it, I think. And part of what they've done is made it a special event for them to be able to come here to our program tonight to see what we're doing. So for those of you who are newer to our programs, the purpose of these programs is to create a forum, a setting in which members of the public who aren't necessarily academics or scientists can hear from scientists and academics about some areas of science and technology that are cutting edge, perhaps raise some interesting ethical issues. And in the process, we hope that the scientists can hear from the public about what their concerns are, what issues they identify, and the public can hear from the scientists about the science, and jointly we can identify not only the problems but possible solutions to those problems. The goal here is to have a thoughtful conversation about these issues, so we encourage everybody to feel free to ask questions and join in the conversation, but do what you can to also be listening to what others have to say in the room. The program tonight is a little bit unusual in that it's a part of a series, and I want you to know that it is not intended that you have to have attended the first, the second, to see the second and the third part of the series. They will be independent events, but they're all on the same topic, which is geoengineering, organized by tonight's moderator, Gerald Mullendorf, who will tell you more about that program. But as moderator generally for our programs, I want to start tonight by reminding you that our goal tonight is to look at something fairly specific. Although there is motivation for thinking about geoengineering, trying to modify the climate of the planet by cooling it, although there's motivation for that based on what we understand about climate change and about the warming of the planet from science, we also appreciate that there is a debate about whether that's occurring and how it's occurring. So although that will be part of the motivation you will hear about tonight, the key questions we want to address in this topic and in this series focus on the geoengineering itself. You could take out all of those issues, whether humans cause warming, whether CO2 causes warming, whether the planet is warming because of human activity or not, and simply ask, what if the planet were to go through a cycle where it were to warm unacceptably to a level where we could not feel we could handle it? What might we do? And that raises questions still about what we're willing to do in terms of the science that we might use. So that's what you're going to hear about tonight. I want to remind all of you, especially those of you who are new, that we have a form on your seats that is very important to us to figure out what we should do for future programs. So let us know how this works or how it didn't work. And other than that, I think we're set to start. So I'm going to hand it over to Gerald Mullendorf, who is a philosopher from San Diego State University, who's been interested in our ethics programs, involved with some of them for, I think, since the earliest stages of these programs. And now he's decided to take a lead role in helping to run part of the series. So, Gerald, I'll let you take over.
Hi, my name is Gerald Mullendorf, and I'm a professor of philosophy and the director of the Institute for Ethics and Public Affairs at San Diego State University. And the Institute for Ethics and Public Affairs is co-sponsoring this event tonight at the San Diego Ethics Center. And as Mike said, it's the first of a three-part series, a discussion on geoengineering, that is using technological means other than reducing CO2 emissions to try to affect a cooler climate for us. And tonight's topic will be about the use of aerosols, whether or not it, or how we might use aerosols to affect a cooler planet. There'll be another session or another installation in the series, another lecture, whatever. We're going to have another one of these in a month on November, I think it's November 3rd. And the topic for that is 5 hard questions about geoengineering a cooler planet, and I'll be speaking at that event, and I'll focus mostly on ethical questions at that event. And then there's a third one further down the road in March. This is a long ways ahead of the plan for you all, but just so you know, Professor Orrin Young, who's a professor of political science at the University of California, Santa Barbara, will be speaking on global governance and geoengineering. So he'll be very interested in sort of the regulatory issues that arise when thinking about geoengineering and how the international community might actually govern such a process. But tonight we are most fortunate to have Dr. Lynn Russell of the Scripps Institute of Oceanography. Dr. Russell is a professor of atmospheric chemistry at Scripps. Her research interests are in aerosol evolution composition and the dynamics in the troposphere. Dr. Russell received her BS in chemical engineering and her AB in international relations from Stanford University. She received her PhD from the California Institute of Technology. Won't you please join me in welcoming her?
Thanks, Daryl, for that introduction. Which slide presentations here, and is the volume fine? Well, we hope so. So, as Daryl and Michael mentioned, my role here as a scientist, and a climate scientist in particular, is to tell you a little bit about what the climate science community is thinking about and concerned about, and so to tell you why people are thinking about trying to do geoengineering and what motivates them. And so to do that, I'm going to explain a little bit about global warming and the basic sort of textbook science that underlies the what is driving the planet in its temperature. And aerosols are part of that, and they're part of our climate. I'll tell you a little bit about what I actually do in terms of research, some of which includes measuring aerosols here in San Diego. And then I'll talk about geoengineering, what it is, and how aerosols might be useful in that. And I'll explain at that point where James Bond comes into this, for those of you who might be wondering. And so global warming is often appearing in the news these days with various humorous and not so humorous contexts. And of course, recently this year, it's been in the news for sort of non-scientific reasons in terms of whether there are things going on other than science behind climate. And so I'm just going to point out a couple of facts that you probably all know. It does not rely on Al Gore. He's not a scientist. He didn't discover it. He has done a great job in publicizing some aspects of it, and for that, the community appreciates his efforts at communication. It's also not a conspiracy. Most of the scientists I know involved in this lose money because of it. It's also not a faith, so it does not matter whether or not you believe in it. It's just a scientific consequence. And what I'm going to do, rather than going through some of the evidence that's been collected that was shown in the introductory slides in terms of measurements of temperature change, I'm mostly just going to focus on kind of the underlying textbook science, which is non-controversial in terms of where, sort of why people are concerned in terms of running out of other possible explanations for what could happen to the future of climate. And so starting the first part of this textbook approach is something you guys probably all know, and you might call it common sense rather than the first law of thermodynamics. But it basically says that energy in equals energy out, plus sources and sinks, minus sinks. And so if you don't have any sources or sinks, what you put in is going to be what you put out. You can't make more heat than you start with. There's certain limitations. And as this applies to the Earth, all the energy on the Earth comes from the sun in one form and possibly with delays. And so that sun gives us energy that comes in during the daytime on half the Earth, And that's going to end up with a factor of 1/4 in the geometry that I'm going to work in there and kind of try and sneak past you, but you can ask me about it later. And then that energy comes out from the Earth in the infrared radiation emitted by the Earth. And so what goes in, and this is short wave, so I call it S, and this one's long wave, so I call it L. And this energy in equals energy out was first kind of formalized by Rudolf Claudius and William Thomson, who was later knighted Lord Kelvin back in the 1850s. So this is not new. The second thing we need to use is some principles of radiation. And basically, the fact that sort of the more infrared radiation that's emitted from an object, the higher its temperature. And so here's like an infrared map that you might see in a TV news broadcast showing weather and temperature. It's kind of, these are both sort of simple examples that aren't totally the most apropos, but the law that governs the planet's emission of energy, so how much energy goes out, is that energy is equal to some fancy constant called the Stefan-Boltzmann constant times the temperature of the mean surface to the 4th power. So that's the amount of energy going out is related to the temperature. In order to get more energy going out, you have to increase the temperature. And this was thanks to the Stefan-Boltzmann law that Stefan and Boltzmann sort of worked on independently and almost simultaneously, so they're both given credit. And it was actually proved much more rigorously by Max Planck 20 years later with a much more quantum mechanical approach. And so this is, if you don't like the weather analogy, the same sort of principle goes into, you know, the infrared night vision goggles. Things that are warmer, like people, emit more and different wavelengths of energy than things that are colder. And so we take these two things together. This was energy in equals energy out, and this one that the emission from the Earth is going to be sigma times the temperature to the 4th. We put these two together, and we find out that the temperature at the Earth's surface should be minus 18 degrees Celsius or 0 degrees Fahrenheit. So that would be really, really cold. So we hope that we've done something wrong in this calculation. And I did use this number here, and I'm going to tell you how I got it later. But 239 watts per meter squared coming from the sun, and I chopped this part off, and I'll tell you why later. But what I've done is just assume that what comes in is equal to what goes out. So that would be a really cold mean temperature. That would put us all looking a lot like Minnesota, which has drawbacks. So what we'd like to understand is how we actually get to our actual mean temperature here on the surface, which is about 15 degrees Celsius. So this is globally average mean surface temperature. And we do this because we forgot something when we just let all the energy go straight out. We forgot the greenhouse effect. And what that does, and what was shown by John Tyndall in 1858 in an experiment in a laboratory where he put CO2 first and then also water vapor and a few other gases in the laboratory, is that he showed that those gases absorbed some of the energy, just like our atmosphere does, and emitted it back in both directions, so that you actually got more heat coming back to the surface than was initially coming in. So that on the left-hand side, we have to add this other term, this flux from GHGs, or greenhouse gases. And water is, of course, a natural one, and some CO2 is also natural. And this is what we need that effect in order to get us to the 15 degrees Celsius. And so, and this, of course, was well known and has been shown in a number of different works back in the 19th century. So what have we added to this? Well, the thing we've added is that since then, some of the CO2 that's been in the atmosphere has increased. And so up to about now, it's maybe 80 or 90 parts per million volume is this metric of concentration. And so that's about a third increase, so 30% increase from what it was back in 1960. And so that amount of stuff that's absorbed and emitted back, increasing that GHG part, has gone up. And so how does this have to work in terms of the first law of thermodynamics? That as this number increases, then the temperature of the planet is going to go up. So as you increase the greenhouse effect, you get an increase in temperature. So, but I'm going to go back to what I skipped before. Oh, no, wait, sorry. So first, this is sort of a more traditional, I'm going to relate this back to what you've probably heard of in terms of why it's called the greenhouse effect. This is how greenhouse works, that the glass is largely transparent to the incoming shortwave radiation from the sun. And then it's absorbed and emitted as long wave, but it's not transparent to the long wave. And so here it's absorbed and emitted in both directions. And so the water and CO2 in the atmosphere are acting in the same sort of way. So this is kind of the physical picture that we have in addition to that textbook picture. And so this is, again, part of the greenhouse effect is natural. We would be much, much colder. We would be at minus 18 degrees Celsius if we didn't have the greenhouse effect. If by adding extra CO2, we enhance the greenhouse effect and get a warmer temperature. So that's the first basic idea. So where do aerosol particles come into climate? And first of all, it was the previous slide told you a little bit about aerosol particles. This is particles, particles, particles. These are actually sort of too big for aerosol particles, the dust that we sweep up in various places, and the kind of particles that particle physicists talk about making in cyclotrons and synchrotrons. Those are too small for the particles we care about. So the particles that I'm going to be talking about are somewhere in between. And to give you an idea of how big that in between is, this is a human hair. You can use your own as an example. Its diameter is about 100 microns. A micron is a millionth of a meter. And so a typical aerosol particle is a little smaller than 1 micron in diameter. And so that's 1% of the width of a human hair. And so, and just to compare, rain is kind of on the big side. Those are the ones that get so big they fall out. They are between 20 microns and sometimes up to 5 millimeters, but that's pretty big. And so those are the particles we're talking about. What are aerosols? Well, they certainly include, this is an example of an aerosol you can make in your home by spraying a compressed gas with a fluid. But there's a lot of aerosol particles that are emitted over our planet, some by combustion processes, burning wildfires, trees, as well as fossil fuels, and some dust gets lofted over various regions of the planet. And you can actually see from space how these particles, dust particles, lift and how long they stay in the atmosphere so that they can be transported hundreds of miles. And so the particles we look at are mostly from a few really big sources. Some of them, again, are natural. Ocean waves breaking give us marine particles. Forests emit particles. Some fires are natural, and those have a number of particles whose plumes we can, again, often see from space. And ships, you might have noticed, also have plumes coming out of them, as do some power plants. And so these are where most of the particles in our current atmosphere come from. So how do we measure these, since this is actually what we do? We go out and put a sampler on top of a ship or at a pier and bring particles into an inlet and either collect them or use an instrument online to actually look at how many there are and what they're made of, and get samples that look like this, where we have particles collected on little samples that we can then take to microscopes and other chemical analysis. And we've done a lot of measurements at the Scripps Pier here in San Diego, so a little bit offshore of the coastal zone. And what we found is a variety of aerosol particles coming from a number of different places, sometimes from up in, so Los Angeles is sort of up this direction, and the Port Bella in Long Beach tends to bring us a lot of what we call sulfate particles containing sulfur. We've been looking a lot at combustion sources in the riverside area, and they tend to produce a lot of particles that are carbon-containing, which we call organic, and that even have mixtures of nitrates and carbon called organonitrates. And so the red spots show kind of the hot spots of where, during any particular sampling day, that air was coming from. So these are the different trajectories. And so that's just one example of the sorts of aerosol particles around here. But why are aerosol particles important for climate? Well, again, the answer to this you would probably call common sense rather than some fancy law. But you already know the answer to which of these two cars you'd like to be sitting in on a hot day without air conditioning. You'd like to be sitting in the white car because it reflects energy and sunlight better. Some people have jokingly called this the White House effect, depending on their political persuasion at the time. But the important point is that the black car is better at absorbing the heat, and the less black, the less absorbing. And so what we think about is that this car here is going to get hotter than this car here. And it's because what's going on here is called reflection of the light. And that's where the light is actually just changing directions and bouncing back into space. So how does this affect the planet? So imagine the Earth is a big car with different colors on it. So we've got some parts of the Earth that look a lot like the black car, and some parts of the Earth that look more like the white car. So clouds tend to be fairly white. That makes them very reflective of sunlight. Oceans tend to be very dark. They tend to absorb a lot of heat. Land is very variable. Dark green is good at absorbing. Deserts are much more reflecting. But clouds and aerosols, these both act like the white car and reflect energy back to space. So what does this tell us then? This tells us that in total, if we add up all those land and aerosols, 31% of the sun's energy on average is reflected back to space. And so I use this number down here, this 239, to do my earlier calculations. But what's really coming in from the sun is 346 watts per meter squared. And this fraction, this 31%, is sent back from this White House effect. This is our greenhouse effect here. And so that is where that 239 came from. So what does that mean? So if we think about this the same way we thought about the greenhouse effect, and we put our little White House effect in here, where we're subtracting this fancy alpha, which was just that sum total 31% of reflecting, then that means that as you add more aerosol, you would get a cooler planet. And so that would be one way to cool off from where we are currently by increasing aerosols. Then more sunlight is reflected, less infrared is emitted, and the temperature of the planet at equilibrium decreases. And so that's their current rules at what we understand. And you put these two together, you can kind of think of these knobs, where this is what controls the system, intentionally or unintentionally. As you add greenhouse gases, you get a warmer planet. Aerosol and other ways to change the color of the surface are going to potentially cool the planet. And so aerosols do this in two ways. One is just when the sunlight hits one of these tiny 1-micron droplets, they're actually really efficient at scattering that light back and reflecting it. And that actually increases in high humid conditions. And again, you guys have all seen this before when you've driven through LA's smog. The very fact that it looks gray and icky, right, rather than clear sky, that's because the sunlight is reflecting back to you. And so if rather than imagining you stood down here looking at the smog in front of you, if you were up in the sky, that would be where the light is being scattered back into space. And so this is a very clear, well-understood effect. There's a slightly more uncertain effect where particles, when you increase particles, you actually change how clouds look too, because you increase the number of droplets in the cloud, and that decreases the average size of the drops, because you still have the same amount of water, And it gets them closer to about the magic 1 micron, which is the wavelength of the incoming sunlight. And so that's the second effect. And so these are the two things that aerosols do, and here's the fancy way to summarize all this in terms of what these knobs are. And this was put together by the Intergovernmental Panel on Climate Change, and this is part of what the 2007 team earned the Nobel Prize for, was awarded the Nobel Peace Prize. And what is shown here is what they're trying to do is sort of compare some of these warming and cooling effects. And I'm just going to focus on these top two here, which are the greenhouse gases. And they're in red, and they have positive radiative forcing of 1 to 2 watts per meter squared because they're warming effects, so red for warming. Down here are the two aerosol effects, and they're blue for cooling. And if you just kind of eyeball it, maybe if you added up those two blue bars, you'd almost offset most of the CO2 and maybe a little bit of the other greenhouse gases, methane and nitrous oxide and halocarbons. But what I really want to point out in this diagram, before we sort of start thinking about being able to turn too many knobs at once, is that in greenhouse gas effects, in terms of how we understand the warming and what its effect on temperature is, these are the error bars, or the uncertainty. This is how much we think it could vary from our best guess. Over here, these are the bars for the aerosols. So you'll see that they're much bigger than the actual bars themselves. So there, the guess is not so good, right? The guess is very uncertain. And so, to sum up, what we know is that carbon dioxide traps sunlight like a blanket. Atmospheric CO2 has increased in the 20th century, so it's kind of making us a thicker blanket. And the Earth's temperature increases like the person under that blanket. We also know that aerosols cause cooling, and could it be enough to offset warming, perhaps more than it already has done, in a way that we could control. But there are things we don't know about climate. We don't know, will the temperature increase in 20 years or in 100? Will it increase more in Siberia or in California? Will sea level rise? Which species will adapt? Which communities will adapt? And will aerosol changes cause less rain or less snow and other more complicated meteorological consequences? So that's where sort of the textbook understanding has to rely on a number of complicated and uncertain models. And so when we think about aerosols for geoengineering, I mean, the first thought is maybe, well, we've made this, we have a problem and we want to clean it up. And so how do we go about doing that? And I guess I'd say that more generally, most of the climate science community has, well, is concerned not so much about some of the average trends, but of certain specific, less predictable events. And so there are things that could happen more rapidly than average increases, such as the loss of sea ice, which, and this is just comparing the sea ice extent in 1979 with this red outline, and then this is actually in 2002, and it has recovered some since then. So again, it's a less predictable event. There's some inherent noise in that system. And so if the sea ice were to decrease, well, why are we concerned about that? And you guys probably already recognize why that's a problem, because sea ice is white and the ocean is blue, right? So as soon as you get rid of that white part, not only, do we lose polar bears and things like that, but we've increased the amount of dark area of the planet, and so there's more energy coming in. So we actually there are events like this that could accelerate global warming. And these are the kinds of events that could pose short-term threats that might be worth thinking about a short-term fix for them. And so most of the interest in geoengineering is along these lines of a short-term fix. and I'm going to draw an analogy later on between thinking of this as like buying home insurance or fire insurance, right? Is there anything that, in retrospect, we would have wanted to have tried to do to avoid these things, as opposed to, and not precluding, reducing CO2 emissions is more like sort of saving for retirement. We have to do that anyway. We have to do it at the same time as buying insurance, and one doesn't replace the other. If you have insurance, it doesn't give you retirement. So, so they're two different things. And so that's the basic premise, where the argument is not that we should do or think about geoengineering instead of reducing CO2, but that we might want to do it in addition to reducing CO2, especially if it takes a while to reduce CO2. So geoengineering is usually defined as the intentional modification of the Earth system, and typically it's a method to offset global warming or greenhouse gas warming, and usually by means other than reducing greenhouse gas emissions. And so it's usually at a net cost, but equivalent carbon dioxide savings. So if you were thinking of increasing aerosol particles, so you're increasing the cooling, then you'd think about sort of how much warming that would offset. And so the next question is, well, how would we do this? So here, Hollywood has an answer. If you watch very carefully and pay attention to the plot, which was sort of hard to find, in the James Bond movie, the central idea was that the bad guys had this new satellite called Icarus, which was an orbital mirror satellite. And their idea was actually to use this satellite to bounce and reflect sunlight from the energy, but to target it in some really cold place and sort of terraform it and make it habitable and hence take over the Earth or something like that. But that was the idea. And it's that same sort of technology that's proposed in some of these recently proposed geoengineering schemes, except there the idea is rather than putting it someplace cold on the Earth, you'd actually just bounce some extra energy back into space, and that would offset some of the warming by having less incoming. Of course, and I'm not going to have the time to go into all of the details for all of these, but you might be concerned that by doing that, you're reducing incoming sunlight, and so photosynthesis is also going to be reduced, which might affect our ability to produce food and other crops. So that's one idea. The aerosol ideas are similar in that they also reduce incoming sunlight and bounce them back into space. I'll just mention a couple others. One is to increase the number of trees on the planet to increase CO2 uptake. There's some that take CO2 emissions either at production or, in the power plant, or some actually try and capture CO2 from the air and pump them down into the sea. And there, the idea is actually, in many ways, much more straightforward, because you're actually removing the thing that you didn't want in the first place, and so there's sort of less potential for unintended consequences. You're just reducing the CO2 down to what we know it was before. And the only real concern, other than the cost at the moment, is that you need a place to store all this CO2 where it won't have other ramifications for the planet and its ecosystems. The two I'm going to sort of talk a little more about today, and again just briefly, because most of these are largely at the stage of kind of Hollywood gizmo ideas. But one idea is to use airplanes to bring additional sulfate particles into the stratosphere, which is about 15 to 20 kilometers above the surface, which is where volcanic aerosols tend to be emitted and reside based on natural volcanic emissions. And what we've observed in past volcanic emissions is that there is a cooling of the Earth's temperature during these emissions. And it can be significant, so if you had enough planes and enough particles and you kept replacing them, you could offset some of the warming. The other one I'm going to talk about, the drawing here is a little misleading, because people are talking about putting extra particles in clouds over the ocean and in very low-level clouds. And so the idea there is to use that effect of particles on clouds in order to make the clouds brighter. So only the existing clouds are modified, and they're only modified over the ocean where people don't live, because one of the main drawbacks of aerosols is that they're also bad for our health. They are bad to breathe, and they cause a number of pulmonary diseases. So we don't want them near us, but if they were over the ocean, and we could put them in regions where there weren't people living, then it would allow, again, more sunlight to be reflected off of those particles. And so those are the sort of two main themes. I'd say at the moment this one is sort of greater in popularity, and the main sort of consequence that I think hasn't been explored there yet, it's been estimated that it could work. The consequence that hasn't been explored is how that might change the thunderstorm systems and other storm systems below these aerosols. Since they're so high up in the atmosphere, they might be able to have sufficient cooling to affect storm systems. And so that's one of the reasons that these become much more attractive, because by keeping them over the ocean and in the lowest kilometer rather than 20 kilometers up, they're much shorter lived and they have a much shorter lifetime that makes them easier to control. So all that being said, the idea here is in our simple little model that, again, as greenhouse gases continue to increase the temperature, we can use aerosols, at least temporarily, and perhaps targeted over areas like the Arctic, where we are concerned about sea ice loss and where that sea ice loss has these potential feedbacks that are not easily foreseen. So, but coming back to what we should think about in terms of these ideas, they are very preliminary, and all I want to point out here is, again, the error bars. This was the most uncertain part of the climate energy balance, right? These have the biggest error bars. This is the net down here, and most of this error comes from these two aerosol effects. And so if you were to say, try and do something intentionally, it would seem like you should pick something that we know more about rather than something that we're not so sure about. And so that's certainly a large concern. And so what is the state of the science in terms of will aerosol particles, or could they be used to prevent global warming? I do think it's been shown that they have slowed global warming until now. And so we have them, so thanks for that. But whether they could be used to intentionally offset greenhouse warming, I would say the state of the science is that we don't not yet know how to use particles for geoengineering, and we shouldn't try until we have done the experiments and the modeling to understand what their effects might be. So I think that's kind of where the science is at, and I would say the other proposed schemes I showed are also at that stage. Most of them are sort of on the drawing board. There aren't yet good cost estimates or engineering drawings or implementation plans for any of them because of similar uncertainties in part of what is proposed to be done. So just to wrap up, because I think I'm out of time, what does the science tell us about geoengineering, and a little bit about where I think, some of the key ethics questions that come up because of that science are summarized here. And so global warming, it's not a belief, it's a scientific consequence. We need to do it soon, and we need to reduce CO2 emissions in order to really reduce global warming permanently. And we can do that with clean tech and recycling and lifestyle changes, and we can all do this, even in our sort of flooded, busy lives. But while the basic science for global warming is known, many quantitative details cannot be predicted, and so we should prepare our communities. And so just like wildfires that cannot be foreseen, some impacts and locations of climate change cannot be predicted. So assessing other ways to reduce the consequences of global warming is one aspect of geoengineering, sort of like buying insurance for the changing climate. And again, my little, message here: buying insurance isn't the same as saving for retirement. We still have to do both. And I think, part of the ethical debate until now has focused in the scientific community upon that idea that there could be this moral hazard, that if people do one, they won't do the other. And so that's the first premise. And then geoengineering relies on the same science as climate change and has the same types of uncertainties. And so such uncertainties make the ethical questions more difficult, I think. So scientific research can contribute by finding out, if it can, ways to offset global warming. And finally, the focus of this series is more on if we can, should we. So now the risk of geoengineering may be worse than the need, but some cures may become more attractive as consequences become worse. And so that's just where I would leave the perspective for now, in saying that what I think scientists are interested in doing is being prepared for other alternatives if they're found to be important. But I think it's certainly time to start thinking about how we would decide how they should be implemented and what the criteria for that should be. So with that, I thank you for your attention, and I'll let Daryl.